Hi everyone, this is Unit 2, subsection Monte Carlo versus temporal difference learning. The last thing we need to discuss before diving into Q-learning is the two learning strategies. Remember that an RL agent learns by interacting with its environment. The idea that given the experience and the received reward, the agent will update its value function or policy. Monte Carlo and temporal difference learning are two different strategies on how to train our value function or our policy function. Both of them use experience to solve the RL problem. On one hand, Monte Carlo uses an entire episode of experience before learning. On the other hand, temporal difference uses only a step to learn. We'll explain both of them using a value-based method example. Okay, so natural questions is what's the difference between an episode and a step? Supernatural question to have. It's a question that I have now. So Monte Carlo learning at the end of an episode. Monte Carlo waits until the end of the episode, calculates g of t, the return, and uses it as a target for updating the value of state t. So it requires a complete episode of interaction before updating our value function. In the diagram, the Monte Carlo approach, Monte Carlo waits until the end of the episode, then calculates g, uses it as a return, uses it as a target for its value or policy. Okay, so the new value of state t, the former estimation of value at state t equals the expected return starting at that state. Okay, so this is the former estimation, this is the new value. So it's the former estimation plus some learning rate, and then the return at that time step t minus the former estimation of the value at state t. Okay, interesting. So if you take an example of, the cat and the mouse example, where the mouse is surrounded by one piece of cheese, and then here's their plus 10 or plus much more of the cat. We always start the episode at the same starting point. The agent takes actions using the policy. For example, using an epsilon greedy strategy, a policy that alternates between exploration and exploitation. We get the value and we get the reward and the next state. We terminate the episode if the cat eats the mouse, or if the mouse moves more than 10 steps. At the end of the episode, we have a list of state, actions, rewards, and next state's tuples. For example, state tile 3, bottom, go left, +1, state tile 2, bottom, and then, right, so this is the state. Given this state, let's say it takes this action, go left. With that action, let's say it gets this reward, +1. With that reward, we're in this next state. The agent will sum the total rewards to see how well it did. We'll then update the value of that state based on the formula. So the new value of the state is being created by the old value of the state plus learning rate times, this factor. Then start a new game with this knowledge. By running more and more episodes, the agent will learn to play better and better. Right? So this is the Monte Carlo approach at the end of the episode. Okay, so the episode is like when this is all terminated, right? So when the cat eats the mouse, or the mouse has moved more than 10 steps. And then when you play that out to the termination, you have a list of what happened, right? You have this history. You have a list of the transitions here, and that's what you'll use. For instance, if we train the state value function using Monte Carlo, we just started to train our value function, so it returns 0 for each state. Our learning rate is 0.1, and our discount rate is 0, no discount. Our mouse explores the environment and takes random actions, right? So in the beginning, the mouse has no conception of what has value. Each state has a 0 value, so everything is, moving left is just as good as moving right. moving up is just as good as moving down. So the mouse made more than 10 steps, so the episode ends, right? So we just started a train of value function, so it starts at 0. We have a learning rate and we have a discount rate. The mouse explores the environment, takes random actions. The mouse has made more than 10 steps, so the episode ends. So we have a list of what happened. We know exactly the reward for these things that have happened, right? So we can calculate it now. So the new value at state 0 is the old value at state 0 plus the learning rate times the reward that was achieved minus the old value here. So it's 0 plus 0.1, which is the learning rate, times 3, because it eventually, in this example, accumulated 3 reward because it randomly fell into this path and ate 3 pieces of cheese. And now our new value of the state is 0.3, right? And the learning rate is just a way to discount where is it? So the learning rate is just a way to discount these rewards here to kind of dampen the effect of any single reward instance on the overall value of the state, right? So this is a regularization factor. Perfect. So the Monte Carlo approach calculated the return of g of t. This is what it is. This is just what we saw above in a very nice slide. And that's the Monte Carlo approach. Perfect. So temporal difference learning at each step. So temporal difference, on the other hand, waits for only one interaction, one step. So s t plus 1 to form a TD target and update the value of the state using the reward and the gamma times the value of the state at t plus 1. The idea with TD is to update the value of state at each step. But because we didn't experience an entire episode, we don't have g of t expected return. Instead, we estimate g of t by adding the reward at t plus 1 and the discounted value of the next state. This is called bootstrapping. It's called this because TD bases its update part on an existing estimate, the value of s of t plus 1, and not a complete sample of g of t, right? So temporal difference learning at each step. Difference here is, we lose this g of t, the g of t no longer exists. What is here now, right? So the new value, what's contributing to this new value is this former value plus the learning rate times, the reward of t plus 1 plus discounted value of this next state minus this former value of state of t. So this method is called TD0, or one-step TD, update the value function after any individual step. Okay, and this slide is what we see above. If you take this example, instead of the 10 winding steps that you saw before, we just have this single step. So the mouse moves left, right? We assume that's random. We just started the train of value function, so it returns 0 value for each state. Our learning rate is 0.1. Our discount rate is 1, so there's no discount. Our mouse explores the environment and takes a random action going to the left. It gets a reward, and that's 1 because there's cheese all around it, so it's going to get this reward 1, right? So going left, reward 1. Keep that in mind. So we just started the train of value function. So this is what we saw above in a prettier slide. It gets plus 1 reward, which is this cheese, right? So we can now fill in these numbers, right? We've assumed that the value of all states are 0, right? So let's figure out this new value of the state. So here we thought that was 0, and then learning rate is 0.1. The reward is 1. It got the cheese. The gamma is 1 because we're doing no discount. The value of the next state, is 0. The value of this, so everything was 0. So there's a lot of zeros in this equation here. So even this gamma times the discounted value of this next state, this S1 here, it's 1 times 0 because we thought that value was 0, right? So this is 0.1 times 1, This is the value of S1 now, right? After one step. After one step, we know that this value is above 0 because actually even taking that one step got us some value. So we just updated our value function for state 0. Now we continue to interact with the environment with our updated value function, right? So now we have everything is 0 except for this particular state, which has 0.1 value. So if we summarize with Monte Carlo, we update the value function from a complete episode, and so we use the actual accurate discounted return of this episode. TD learning, we update the value function from each step, so we replace GT that we don't have with an estimated return called a TD target. Right, this is the TD target. Right here is a TD target factor. So you can see that they're almost the same function, except G of T is replaced by these two. So let's move on to the midway recap. This should be short. Before diving into Q learning, let's summarize what we just learned. We have two types of value-based functions. State value function outputs the expected return if the agent starts at a given state and acts accordingly to the policy forever after. An action function outputs the expected return if the agent starts in a given state, takes a given action at that state, and then acts accordingly to the policy forever after. In value-based methods, rather than learning the policy, we define the policy by hand, so something like greedy, epsilon greedy, and we learn a value function. If we have an optimal value function, we will have an optimal policy. There are two types of methods to learn a policy for a value function. The Monte Carlo method, we update the value function from a complete episode, and so we use the actual accurate discounted return of the episode. The TD learning method, we update the value function from a step. So we replace G of T that we don't have with an estimated return called TD target. Right, so these are the two differences. The episodic has some terminal value, and this is what we are depending on for Monte Carlo, and the temporal difference, we're doing it on every step. So there's also a quiz here. We can take the quiz. Some people skip it, but I think it's good to just look at what is being tested. What are the two main approaches to finding an optimal policy? So we've only learned of two. Maybe these two exist, but the two main ones that we learn is a policy-based method, where you're learning the policy directly, and the value-based method, where you are getting the value of each state. What is the Bellman equation? Well, the Bellman equation is solving a problem that we had in the past where we thought that the computation was n squared. The Bellman equation gives us some recursive O of n version of it. At least that's how I saw in the diagram. It looks like it helps reduce this computation, right? It's the equation of a recursive computation that works like this. Instead of starting from each state from the beginning, calculating a return, we could consider the value of states as this recursive function. And yeah, so here's a picture of it, right? So the picture of it allows us to see that the value of the state equals to the expected return at this policy pi, and we have the return of t plus 1 plus gamma times the value of the next state, right? So in the formula that they have, well, this is the quiz, so they're not going to have a picture of it, but you had this mouse. I think that's a mouse. That could be a cat, but you had this mouse or this cat, and it can go some type of path. And for the Bellman equation, the value of certain things, so the value of this is just a reward that it can get from it, right? The reward of t plus 1 plus 1, right, plus the value of this, right? So the value of this state, let's call this 0, equals the return of t plus 1 times, you know, whatever this is, the value of S1. Is it times or is it plus? Plus, plus, plus. It's the times is actually the gamma, right? So it's plus, I don't know how to draw the gamma of this other factor, given the state. What is this? Oh, yeah, this is just what we saw before. What is the difference between Monte Carlo and temporal difference learning methods? I mean, we literally just saw this, but it's something like this. TD learning, define each part. I don't know. We saw this just 10 seconds ago, but this new value of the state is being driven by the old value of the state plus some learning rate, and instead of the g of t factor, we have the reward of t plus 1 plus this gamma times the value of the next state, and it's being subtracted by our previous opinion of the value of this state, right? And then Monte Carlo is just different in that g of t is the actual sum of all rewards, right? Because it's episodic until the terminal state. We actually know the value of everything, right? So, going back to the example that we had, if there was like, plus 1, plus 0, plus 1, plus 1, plus 0, plus 0, and then terminal, then we know that the discounted value, assuming that there's no discount rate, or the discount rate is 1, is that this is 3, right? And this makes G 3 in this equation. Okay, great. So next we learn about Q-learning.